So the sky is not the limit. I'll try to be a little different to talk today. It's going to mix a little bit of my personal life with my research, because this is something that I've been doing the past couple of years, and it makes things a little lighter, and also you can get a little bit inspired by it. So the sky is not the limit. I love to start with this particular image, which is a Hubble telescope photograph. So Hubble did not take this photo. The astronauts took this photo. This is the last photo the astronauts took when they went to serve Hubble a few years ago, in 2009 already. So it's a long time ago. And I also like to show this photo because it shows that the Earth is not flat. So the sky is not the limit. I, like most of you, started enjoying. Yep.
Sí, dígame.
So, sorry, I thought you were talking to me. So I started enjoying science fiction and seeing myself as a scientist at a very young age. So I liked all the science fiction that you all liked it, probably. And I had a big inspiration from Carl Sagan, and I loved Cosmos and all that. And I loved space missions. And at that time, there was a particular one that was called Pioneer 11 that was sending images from space, from Jupiter, from Saturn. And I really wanted to know how those images got here. And that's one of the reasons why I became a scientist, why I decided to do astronomy. I also like soccer. I'm a Brazilian. So that was my favorite soccer team, Flamengo. And I also like music, and this was the rock and roll guy of my times, Peter Frampton, and I loved him. So I used to write this. I was like 14 years old when I used to write this in all my notebooks. And so this was really an inspirational time for me to go and study astronomy. And I did that as a major in astronomy at the Federal University of Rio de Janeiro. So I'm from Rio. And I did my research work when I was an undergrad at the National Observatory in Rio as well. And at that time, as a young undergrad, I decided I wanted to be an extragalactic astronomer, and I started studying galaxies. And I did not want to study those planets that actually inspired me to become an astronomer. I wanted to really study things that were far away. And I wanted to study things that were particularly exotic. So I started studying colliding galaxies, so interacting galaxies that are going through collisions. So of course, these images are not from my work, but they are images that were taken much later with the Hubble Space Telescope, much later after I was already a PhD. But I did my research work on interacting galaxies always. So interacting galaxies have always been part of my PhD. It's been part of my science, and I'll show you a lot of that coming. And also later, I started studying galaxy evolution in terms of distant galaxies, and I'll show you those images in a minute too. So when I was a grad student, this is me as a grad student observing in La Silla in Chile at the European Observatory in Chile. And I was studying interacting galaxies, colliding galaxies. Then I defended my PhD and I became a postdoc. And when I was a postdoc, I spent time in Chile again and in Rio. And I was also a postdoc at Cerro Tololo for a while. And when I was back in Brazil at the National Observatory as a postdoc, I discovered a supernova 1997D. And I'll tell you a little bit about this because I think it's kind of interesting how you sometimes not expecting something and it comes to you, right? So again, now I'm not with that short hair anymore because now I that was when I was a PhD student. Now here I am already a doctor. So I went back to the same observatory, the same telescope, observing colliding galaxies again. Let me tell you a little bit about this telescope. I've always been very interested in telescopes. I thought, I'm an astronomer, right? So I'm supposed to really enjoy and have control of this. It's so exciting. So this is a small, relatively small telescope. So 1.5 meter telescope. this telescope does not take images, it only takes spectroscopy. So it has a spectrograph. Actually, by the way, it doesn't work anymore. All the smaller telescopes have been decommissioned in La Silla. But anyway, at that time it did. This is 1997, a long time ago. Some of you are not even born yet. And it has this small finder. And this finder is actually connected with the instrument you use to take the spectrum of the object. And all you see is a little tiny screen where you're going to center the object that you're observing. And that's the image of the finder. So when I was observing one of my colliding galaxies, and here it is, it's a small galaxy that belongs to a group of other galaxies that don't show here on this finding chart. So this is like a chart I brought with me from Brazil, because this is what I used to be very organized, not anymore. And this is the object that I was observing. And at that point, when I looked at the guider, I had to center the slit of the spectrograph. And I noticed there was an extra star, and I even wrote here, I don't know, objeto brilhante na direção do eixo maior, a bright object in the direction of the major axis. Now, even drawing here, that was a conclusion I took from what I saw on the tiny little screen that I was centering. So I was actually very curious, was I in the wrong place? Because there was an extra star there. I couldn't see this object from the finder. Just have that in mind that I couldn't see the galaxy because the finder is a very small little telescope, right? So, but I calculated where it was and kind of got here. And I was like, wow, that's interesting. So I decided to take the spectrum of that extra star that was there. And actually, but this is an interesting story because I had a boyfriend who was also in the mountain, and he was observing in the radio telescope. By the way, that boyfriend is Tommy. Tommy is my husband after so many years. But this is, Tommy came to actually give me a sandwich because he was going to go to bed because it was around midnight, and he is a radio astronomer. So he observed on the earlier part of the day. So he came to give me that sandwich, and I told him, I think I discovered a supernova, because I thought, what is that object, right? But at that point, we did not have this yet. So I had a 20-minute integration time. So you have to wait 20 minutes to catch all the light and then add all the light and produce the final spectrum. And this is the spectrum I got. And when we look at this, and I told Tommy, oh, that's a supernova. All these lines were really broad, and it's very different from the spectrum of a galaxy that we are used to. It. So it is a supernova. And the following day, I actually saw the image of what I had discovered, and it's this. So this is the supernova 1997D. And people tend to ask, and if you're not an astronomer yet, if you're thinking of following a career, people will ask you that all the time. They'll ask you, have you discovered something? So when people ask me, have you discovered something? I actually don't usually say, yes, I have discovered something. I say, no, I actually saw a star dying. So a supernova is an explosion. It's the last step, right? The star is gonna blow up, and that's it. What's left is either in this type of stars, because it is a type 2 supernova. The one that was presented before, they were type 1A, so that's a little different. But type 2s, massive stars that blow up and either make a pulsar or a black hole, right? So this is a galaxy that is 53.8 million light years away. So the light that arrived in my telescope that night on January 14, 1997, left the galaxies 53.8 million years earlier. So it's an impressive thing if you think about it. So, but supernova 1997D is actually a famous supernova. It became famous because it is one of the faintest ever discovered. For a while, it was the faintest. Today, there was some kind of contenders that are as faint, but this is an interesting plot that I don't work with supernovas, so this is not my work. This is actually a review by Nomoto et al., 2003, where he plots here kinetic energy versus the mass. And then he plots all types of different supernova here. And if you see the one with the least kinetic energy is supernova 19S7D. It's important when you discover things that have the lower or the higher of something, right? If it is the faintest, then it is setting the parameter for that particular category. So here we have becomes a neutron star, it becomes a black hole, and 1997D is kind of on the decision-making process of what becomes what. So it was, my father wasn't very happy when I told him that this was the faintest supernova. So I wish it was the brightest. And I told him, well, just have in mind that I actually discovered the faintest with the finder of the telescope. So I'm very proud of the supernova 1997D. So 1997 is an interesting year in my career. A lot of things happened. So 1997 is also when I moved to the US. And I went to work with this gentleman here, Dr. Klaus Leider, at the Space Telescope Science Institute in Baltimore. We still live in Baltimore. We have a strong connection with this institute. It belongs to NASA, but it's based at Johns Hopkins University in Baltimore. So Klaus hired me to be part of a team that's called Starburst 99. So this team put together a software that reproduces the properties of galaxies that are having bursts of star formation. So you may remember that I told you that I like colliding galaxies, interacting galaxies, galaxies that are strange. Well, starburst galaxies are strange too, and most of them are interacting galaxies anyway. So I'm still working on that field that I like so much since I was very young. So this work of Starburst 99, it has a lot of citations. Starburst 99 is a very popular software. So if you ever want to reproduce the properties of your galaxies or the objects that you're studying, please do use our software. It's available online, anybody can use it. So this is what Starburst 99 does. This is actually a little bit of old. Today, it looks a little prettier, but this is what I did when I was a postdoc. So I show what I did. So here we have, in the x-axis, you have the wavelength. So here is 3,000 angstroms, okay? So I have that. I mean, it's not 3,000 angstroms, it's 1,000 angstroms. So it's a log scale, so it's 10 to the 3, it's 1,000 angstroms. So this is ultraviolet. Now you're gonna hear this a lot. You're gonna pretty much understand that that's what I work with. I work with ultraviolet light. So about 1,000 angstroms here. Now let's pick an age, and here's luminosity. Let's pick age, 5 million years. So 5 million years is the age of that burst of star formation. So the stellar population is 5 million years old, and it peaks. If you go here and you follow this, it peaks at about 1,000 angstroms. So it peaks in the ultraviolet. So why is that? It is because still the stellar population is young, and the spectral energy distribution is dominated by the ultraviolet light. So those massive stars have not blown up as supernova yet. So they are present in the stellar population, and they dominate the energetics of the stellar population. After they explode, so after the 5 million years, so let's pick the 20 million years. So there are no more massive stars because they have blown up as supernova. Now the peak is much more to the right. As you can see, it's not really in the UV anymore, but it's getting closer to the optical. So it's a very powerful way of understanding the stellar population of galaxies after the starburst. So I started doing that for distant galaxies too. And this is what I did for, at that time, a famous CB58. CB58 is a distant galaxy at redshift 2.6, 2.58. And it's this little guy here that because it is gravitationally lensed, it's magnified. So, so the brightness is actually not the intrinsic brightness, but it's being magnified, so we see it brighter. So the spectrum of CB58 is actually one of the best signal to noise spectrum that exists, although this galaxy is far away, but it has to do with this magnification effect due to the gravitational lensing. So because this galaxy is far away, it's a redshift 2.5, the Doppler shift has shifted the ultraviolet light into the optical. So if I take a spectrum of this object in the optical, I'm going to be seeing the ultraviolet light because of the red shifting effect. So here is a bunch of models we ran. This is 20 years ago, okay? So I'm giving you an overview of what I've done in the past 20 years. So bear with me. Soon I will get to this year. So CB58 is a distant starburst. And this is the spectrum of CB58. So now we have the models here with different initial mass functions, with different metallicities. And the conclusion of this, this project was that CB58 is a starburst. It's a distant starburst. And things at redshift 2.5 are very similar to things here today, with starbursts today. So when we compare them with the models. So this is something that at that time we were not sure. And today it seems like obvious, but at that time we were just not sure. So then when I was still at Space Telescope Science Institute, and this is something that I tell to all my students and I tell to all of you who are here today, take initiatives. So sometimes you have to kind of put yourself out there and take an initiative if you want to be part of a project, if you like something. And don't be shy, ask, because the no you already have if you don't ask. So if you ask, you can get a no, but maybe you get a yes. And this is what I did. So in 1996, the year before I went to Space Telescope, this image was published, and you probably have seen it. It's the most important image ever taken, and it's on the internet. If you ask Google, what is the most important image ever taken? It's going to tell you it's this image. So this is the Hubble Ultra Deep Field. And this gentleman, Bob Williams, was the one behind the Deep Field project. The Deep Field project is a project that he asked the astronomical community, what would you do if Hubble was yours and you didn't have to compete to get time? So the community told him something that's a bit surprising. The community told him that they would observe an area in the sky that had no bright star, no nothing, and would just let Hubble observe for days and days and days and collect the light and then see what's out there. So many people thought he was crazy of doing this and using his director's time to do that, but he did it. And this is the image he got after, well, the team got after 10 days observing nothing. Thousands and thousands of galaxies. And this image changed our view of galaxy evolution. So now we see that galaxies in the past were smaller and clumpy. But then remember the red shifting story that I told you of CB58, right? When we look at things that are really far away and we're using optical detectors, what we are seeing is the ultraviolet light. So when we see things that are really blue far away, we're seeing the ultraviolet light at that redshift. So when things are really, really, really far away, you don't see the ultraviolet anymore, because what you see now is the color red. So that what you see is the optical that is being redshifted into the high redshift. So this object, for instance, is very likely to be a very high redshift object. So these ultraviolet ones are the UV at redshift 2 or so. But things that are redshift 5, 6, and 7, they are red because the optical have moved to the red. So I have to put all that into account. So this, I was fascinated by this image, and now I am at the Hubble Space Telescope Science Institute working with Starburst 99, and I hear that Bob Williams is doing another Hubble Deep Field, and this time he's going to do the Hubble Deep Field South. So I tell him, well, I sent him an email. And that's what I'm saying, take initiatives. I sent him an email and said, dear Bob, do you think I could be part of the team taking the southern image? I'm the only person from the southern hemisphere here. I could be the representative of the southern hemisphere. There was no such a thing as representative of the south. This was just like an excuse to tell him that I wanted to be part of the team. So he wrote me back the email and he said, you know, when a person is really busy, the emails don't have many words. So Bob's email had one word, welcome. So I joined the team, and the Hubble Deep Field South needed to actually prove that the Hubble Deep Field North wasn't something unusual, right? Maybe we had some kind of bad luck and pointed to a place that was full of galaxies. Now we need to look somewhere else to see if the universe is like that anyway. So the South would be, the Hubble Deep Field South would also point all the other instruments, Hubble instruments, at the same time. So it needed a really large team, and this is the team. And I joined the imaging team, the WIFPIC2 team. So here I am. And you can see there are lots of people here. I'm going to point out this guy here because he's going to show up again. And it's again on that take initiative kind of thing. So, so we put together the images, and here it is. Many people have not seen the Hubble Deep Field South. They have seen the North, but not the South. And the South has actually a very long exposure image of a quasar. So it's a supermassive black hole inside a galaxy that we have the best spectrum ever taken of a quasar. And then we have the image of the empty area in the sky. And this is it. And I have a better quality here. So again, it shows thousands of galaxies in a region that there are no bright stars, no nothing. And there are, you know, gravitational lensing. This is one of them that has a gravitational lens. I just highlighted here because I like them. So anyway, I told you in 1997, a lot of things happened. This is already in 1998. Let me go back 1 year, 1997 again. I got married. And this is important to say too, because you have to balance your life with your career, right? So you're doing these discoveries, you're joining these teams, you're doing all this, and you don't sleep, and you, and it's like, oh, and you still have a life to manage, right? So at some point, you have to make decisions. And the decision is what I call the two-body problem. So Tommy, so this is Tommy. By the way, he's a Scarlet supervisor, if you guys don't know. So Tommy Wickland. So Tommy was a professor in Sweden at that time. And he lived in Sweden and I lived in the US, and we got married in the US. So at some point after the project Star Wars 99 was kind of done, I moved to Sweden. So it was a decision that I made, and I went to work on this observatory, which is an absolute beautiful place. It's Onsala Space Observatory, close to Gothenburg, where Tommy was a professor. And I went on a gender balance program to actually have more women in science and engineering. So it was a fantastic experience. But we decided, Tommy and I, that we like to live in a neutral country, not Sweden, not Brazil. So we came back to the US. And this again, is especially for the young ones. Plans change. you can't just predict your life as, next year I'll do this, in 2 years I'll do that, and that. It doesn't really go always smoothly. And have, courage to change. Sometimes it takes courage to change. So the courage here was to go back to the US. So Tommy actually got first a job at the Space Telescope Science Institute, working for the European Space Agency. And I contacted that guy that I showed you the name, John Gardner, in that full of names. I contacted several people in that team. And I said, okay, I'm going to go back to the US. Does anybody know anybody who is hiring? And John wrote me back and he said, oh, Duilia, we are taking more deep fields with the new camera on Hubble. So yes, we're hiring. So that's when I went to Goddard. So Goddard is, well, there are 10 NASA centers around the US, and Goddard is the one close to the capital, to Washington, DC. So Hubble is a Goddard project. So the operations center is inside NASA Goddard. So I have already this connection with Hubble, and John was part of the team of the Hubble Deep Field South. So this time I already connected with Catholic University because I wasn't an American, so I couldn't work for Goddard and be paid as a civil servant. I had to work as a contractor. And Catholic University of America has an institute inside NASA Goddard, and Catholic University hires people for NASA. So NASA pays Catholic, and Catholic pays the person working. So in that case, me. And that's the institute that we have inside NASA Goddard. So I was hired to work on this project, the Great Observatory's Origins Deep Survey. So now we are taking a lot of images, deep images. Remember, we did that in 1996, then another one in 1998. Now we're doing several, and we're doing with the big camera, the beautiful advanced camera for survey, not the old with Peak 2. So here is the size of the goods image. In comparison, for instance, one of those images of the deep fields is this size. So now we're talking, now it's a large area, right? We are mapping an area of the sky. And there's different footprints here are different instruments that run in parallel when you're observing with Hubble. And John actually hired me to work with the WIFPIC 2 parallels, especially taken during the UDF campaign. So now what is the UDF? The UDF is the ultra deep field. So the ultra deep field is centered on this goods field, and the ultra deep field is the deepest image ever taken. So it's taken with ACS on a large campaign, dozens of days again. And I am in charge of looking at these parallel images to look, because this is the filter, the ultraviolet filter. These images do not have the blue color. So here's the image of the goods image. And it's an amazing image. And every little dot you see here is a galaxy. And this is the ultra deep field. Again, every little dot you see is a galaxy. But I don't know if you noticed the color here is a little red. And it has to do with the fact that we did not use a blue filter in the ultra deep field. We did not use what the U band, we use from B and above. So by not having the U band, we're excluding the ultraviolet color. It's on purpose. It was a choice. We are looking for very distant galaxies. Remember, the red color, everything is going to be red shifted. So we might as well just observe in the redder colors and get those really distant galaxies. So that's the reasoning for not including the blue color in the ODF. But there is a surprise. In a little while, you'll see something else coming up. So anyway, so this is the UDF. So the message on this project of deep fields is that we're starting to understand galaxy evolution. So how galaxies build up their morphology, their shape. So again, for the young ones, when you least expect, something will show up in your life that you didn't plan. So here I am at Goddard. I work on these deep images. I love that. And I'm invited to actually apply to become professor at Catholic University. And I did. So in 2008, I became a physics professor. And I loved it because I was missing tremendously the contact with students. So I've been there since then. Now I'm a full professor in the physics department. I still teach my astronomy course. This is the first time I was teaching that course. And that's the physics department in the building here. And here are some of my students. I'm going to show the results of Amy, Sergio, and a little bit of Fernanda too. So there's two students there from Chile. They're not students anymore. Sergio is actually a professor at the University of La Serena. So they were Chilean students in Brazil, at the University of São Paulo. And Amy Soto, Amy is Puerto Rican American, and Amy was my students at Catholic University. So Sergio and Fernanda worked on one project and Amy on another one. And then I have a bunch of other students here that work with me. So let's just go over. So let me tell you projects that I'm working on. And one of them is called the Blue Blobs. So again, interacting galaxies, right? So here we have, I don't know if you remember when I was talking about Starburst 99, and there was the Starburst galaxies having a lot of star formation. This is one of them, M82. And M82 is in interaction with M81. And actually there's a third one, NGC 377, never shows up because there's a bright star right in front of it. Nobody wants to take a picture of that bright star. So, but it's a triplet. And we know it's interacting. This image here is taken by an amateur. It's not a professional image. It's just the scale is important here. You already see a little dwarf galaxy here, Homburg 9. Okay, this image though isn't the ultraviolet. Remember, I like ultraviolet light because that's where the massive stars are, where the energy is. So NASA had a little satellite called Galax, small satellite, 0.5 meter. Really tiny baby, fantastic detector. If ultraviolet photon passed by, galaxy detected. And this is the image of M81 and M82 seen in the far UV and in the near UV. And you can already see that, look at the Homburg 9 here, you can barely see, but oh my gosh, it's so bright in the ultraviolet, right? Lots of young stars, hot and ultraviolet bright. So I started looking into these objects and trying to understand why it is so different. And it's just such amazing. Look at all this stuff. So I started comparing this with the hydrogen maps. So hydrogen maps taken with the very large array, for instance. So this is an H1 map. So we see the hydrogen, the neutral hydrogen gas, right? It's all over the place. Wow, right? So this is M81, this is M82. This is that galaxy that nobody talks about. Here's Homburg 9. Do you remember seeing anything here? No, because there isn't. There isn't anything here. We're talking here, right? Well, if I put the Galaxy image on top of that, those are the blue blobs. Going back here, so you see little teeny stuff. Oh, here they are. Now I kind of won in the jackpot here because Hubble had observed that region. And we look at the Hubble images, we see what those blobs are. They're stellar clusters. And here they are. The three of them. 3 stellar clusters. So that's that entire area seen with Hubble. By the way, all these galaxies here are really in the background. They're far away, very far away. And these stars are stars in the Milky Way that are in front of it. And these are the stellar clusters, the blobs. So what do? We model them. We want to understand the age, we want to understand their metallicity, we want to understand everything. But we only have colors. We don't have spectrum. This is too faint to take a spectrum. So this is a color magnitude diagram. So this is the red color. This is optical minus red. And then when we do this, we start seeing the stellar population divided into clumps here in the plot. And we're actually able to tell the age of stars by their color. So we start putting what we call isochrones on top of it. And we start seeing the ages of the stellar populations. So here are the young ones. You see 7 million years here, 14 million years, and up to 90 million years, all the green stuff. But we also have an area here that the population is kind of old. So this is kind of surprising, kind of nice. So there are young stars as young as a few million years, and there are old stars as old as 200 million years. We start understanding this environment where the stars are. And then again, I win the jackpot. There is a simulation for it, and this is by Mim. And it's a simulation that shows M81, M82. M82 is the yellow one. The one that nobody cares is the green one. And right in between, you start seeing things that belong to all galaxies. So the area already has material, has stars that were from those galaxies, or gas that was left here from the interaction, so debris of those galaxies that form this new stellar population. So this is the kind of work I've done in the past, let's say, 12 years. And we have a lot of articles on similar projects, which is called the Blue Blobs Project. And we always look at, with galaxies, the ultraviolet light, we look in H1, just look at the gas, and then we do follow-ups with the giants like Gemini. And we sometimes unexpected things come too. So Rafael Freixo, he joined us at some point in this project, and Rafael ended up discovering the largest spiral galaxy. So what Rafael did is he combined galaxy, the ultraviolet light, with optical light of this particular galaxy. And when we measure the size of this galaxy, it's 5 times the size of the Milky Way. So interaction is making this galaxy really stretching. It's a spiral galaxy that's being stretched out. And then we kind of gave it a nickname, Condor. So this is the good news during the pandemic. So the Blue Blobs keep giving papers. So this is the most recent paper. It's a paper published by Sergio and the team, where we're studying this particular group of galaxies. And the result is astonishing too. So this is the image we have. It's a combination of telescopes, mostly Gemini. Actually, this is only Gemini. So the major conclusion of this paper is that we have to be careful when we look at interacting galaxies. Sometimes we think, oh, when we look at this, we think, oh, this one is probably formed because of interaction. So it's probably like a tidal dwarf galaxy that was born out of this debris, just like the blobs, right? Well, actually, no. So the main results of this paper is actually this galaxy is actually a galaxy that, just like the other ones, has the same properties as the other ones, the same type of stellar population. Because if it was formed recently, you would have a different stellar population. So the metallicity is similar to the other galaxies. So this is a triplet. This galaxy has been messed up by the interaction, but it's not a new galaxy born from the debris. So this is an important piece of galaxy evolution, trying to understand how galaxies form the disks, and this is the topic of the next project, the deep fields. So about a decade ago even, 15 years ago. This is how we saw the distant galaxies. We saw them very clumpy. Just remember that this is all in the ultraviolet, because the ultraviolet now is shown in the optical, and all we had was optical detectors. So we start seeing things that were a bit weird, like this clumpy objects, or this, several galaxies here. What is that? And even the ones that look a little bit spirals were weird, right? So what are those? We know they're UV, they're ultraviolet clumps. So when do these ultraviolet clumps become disks? Because we know we're in a spiral galaxy. We see spiral galaxies redshift 1 and lower. So when do these UV clumps actually get together and make the disks? So this is a project that I've been working on several students, including Amy, that I already showed you, Amy Soto. So we know from the merger tree that the disks grow between mergers. There are evidences from that, and there is evidence from the theory also. And from the simulations, we actually see that these high redshift clumps could both dissipate to form disks, or they could form bulges. So this is actually, I love this image. This is a real image, the ultra deep field objects full of clumps, right? UV clumps. And here is a simulation that shows that galaxies that far away should be clumpy. So how did I start doing this? I start looking in the rest frame ultraviolet. And to look in the rest frame ultraviolet, you have to look into redshift 1.5 or lower. And I used a series of instruments with Hubble, a series of cameras, the old with PIC2, the ACS solar blind channel, and the newest, which is already old, the wide field camera 3 with the UVIS instrument. And then we take a deep ultraviolet image with Hubble. So that's the first time that's done. And this is showing the different epochs on top of the UDF, the old ultra deep field. And this is what the HuffPost called the Holy Hubble. So the Holy Hubble is this. And I hope you appreciate how different this is from the ultra deep field when I pointed out that that was kind of reddish. And this one has the blue color. Or there are actually, I think, 23 filters in this image. This is our team that took this image. It's the most colorful image ever taken. And now we added the ultraviolet colors to the ultra deep field. So we start seeing all this little teeny UV stuff everywhere. So we see the clumps in disks that are not even formed yet. So here is Amy with Bob Williams when we presented this work, and Bob was at the AAS, and it's always fun to talk to him. So this is Amy's result of her thesis of 2 years ago. And what she did is that she looked at the optical reddish, the Z band, which is here. And then the Z band is actually at redshift 1.5 or so, or 1 to, between 0.6 and 1.5. The Z band is showing the optical. So the optical, just like the galaxies we see with our visual here in the local universe. But then we use the ultraviolet camera to see the clumps. And we start seeing clumps, yeah. So what are these clumps? These clumps are actually star-forming regions, huge star-forming regions. So what Amy did is she measured, first she had to detect all the clumps. It's a lot of work. You have to come up with a way of selecting the clumps and, thousands of clumps you find. And then you measure sizes. In her thesis, and this is actually a paper that she published just before her thesis, she analyzed about 1,000 galaxies from this Hubble ultra deep field. And she shows that there is a strong evidence of the evolution of size with redshift. So clumps get bigger with time. So to support also, her work supports this clump migration towards the center with time. So that's how you build the bulge. So the clumps go and migrate inwards and form the bulge. So this is kind of a unique result and very, very exciting. This work continues. This was presented at the last American Astronomical Society meeting in 2020 before, before COVID. And this is the result also what we call the UV candles. So candles now is several other deep fields, not as deep, in the ultraviolet too. And we're also looking for the clumps. Now we're looking for larger samples to start to understand better clump migration and all that. It's almost over. So now we have also been doing work with undergrad students. So I like to show this work because I think it's quite special. It's called the Big Data of the Huge Universe. We used machine learning to identify colliding galaxies. So we use Sloan data. So Sloan is a database that is available to everybody. And I had a big team of students a couple of years ago. And we start doing machine learning of identifying colliding galaxies in those databases. And all of a sudden, this project is reborn this year. I am already making another team with 2 students who want to work with me on this. So we're going to be doing more of that. The future is really on the James Webb Space Telescope that's going to be launched next year. And I hope to use the James Webb to understand when disks are formed, the first disks. This is just. And I also work with children. So trying to inspire children to do astronomy or to do science if they like. And I will finish here. If you have questions, I'll be glad to answer. Thank you.